Hello, everybody. Thanks for being here. So today's webinar is going to be a little thought piece that I did originally at the Korea Society for Environmental Health and Toxicology. That was a few weeks ago, and the title was Painting a New Picture of Risk Assessment. So briefly, I want to just give you a little overview of where I'm thinking we're going to go with respect to risk assessment and how we're going to move into next generation risk assessment. So here we go. There we go. So I think we're pretty familiar with what risk assessment looks like today. This is what I think risk assessment is going to look like tomorrow. In my envisioned future, one of the things I did at the Army for several years is I would have to think about what's going to happen in the potential futures that we might have. And so kind of use some of those same skills I learned at the Army to apply it to risk assessment. And what I think we need to see in the future for next generation risk assessment is I think we need to be starting to move towards digital twins. And for those of you who aren't familiar with digital twins, this is the idea that we can have computerized versions of people. So at the Army, one of the things that we had was digital twins of helicopters. And what that allowed us to do was, because we had such really good science on how different materials would flex and bend and how they would stay rigid in different environments, we were able to actually begin to simulate what different kinds of rotors for a helicopter might actually do for the helicopter. We're starting to see some of this same technology come out in the healthcare space. We're starting to see individuals talking about doing this with respect to cancer. Can we create a digital version of somebody's tumor and then in silico look at how the tumor responds to different kinds of cancer chemotherapeutics that we might give? So I think we're going to be able to in the future move into this space for digital twins within toxicology. But for those of us who've been doing toxicology for a few years, we know that in the chemical side, we tend to lag what's happening in the pharma side, as well as in cancer research, and so they're typically 10 to 15 years ahead of us for whatever reason on the chemical side that I'm still not sure about. But anyway, I think this is where we will eventually be able to get to. But to get to this point, we first have to acknowledge where we are. So this beautiful painting, which I did several years ago, is what I'm envisioning. This is what risk assessment today looks like. It's pretty enough, it's standardized. It really hasn't changed for 40 years, right? Risk assessment. Chemical risk assessment, at least in the United States, was codified in 1983 for the most part. And those of us who have been doing this for a while know that risk assessment is really, really, really resistant to change, despite what we've tried to do. But what if we could start all over again? So I'm going to borrow a page from the historians and the philosophers. And one of the things that they like to do is especially in history, they talk about counterfactuals, which is a little bit different than what I'll be talking about later today with counterfactuals. But in history, the idea of a counterfactual is, what if history didn't actually happen the way it happened? What if history took a turn? So what if we were to wipe the slate clean, as you see here? So my picture is now gone. And we had an opportunity now to do a new picture of risk assessment. We can now paint on this canvas and we can create what we think risk assessment should look like. What if we could start this all over again? So this is kind of the start fresh approach, right? So like I said, in history, this is called the counterfactual approach. So we're wiping the slate clean and we're going to make some assumptions. We're going to assume that we have no history of animal experiments, because I don't want to bias us, with respect to what our previous history is. So what we're going to say is let's imagine we don't have this history of animal experiments for toxicology. We might have animal experiments there, but we haven't really used them for risk assessment, is what I mean by that. Probably the biggest assumption we have to make is imagine that the 1983 NRC report does not exist. For those of you who aren't in the United States, the NRC is the National Research Council, is part of the National Academies of Science, Engineering, and Medicine. And back in 1983, they released this report, Risk Assessment in the Federal Government, Managing the Process. And this is kind of the start of risk assessment in the United States. And this is what set the stage for all of the documents that came afterwards. And most of us today are familiar with the Silver Book. So Had this 1983 report not existed, the Silver Book probably also wouldn't have existed. Now, let's also imagine that we've never regulated chemicals in consumer products before. That's a kind of a big one. I imagine we never regulated drugs before. So what we're imagining now is we've really never done toxicological risk assessments, right? But we are going to imagine that we have all the tools that we have today. So we have our in vitro, we have animal studies, we have omics tools, we have all these different things available to us. We've just never done risk assessment with them. So we're going to imagine that these cell-based and in vitro methods exist, right? We're going to imagine also that we have ultra-fast computers, which we didn't have in the 80s. And we're going to imagine that we have our current theoretical knowledge of biology. So we understand how certain things work in biology. We understand the basics of biochemistry. So we haven't lost any of that knowledge. Michaelis-Menten still came about in the 20s, and it still exists today for the biochemistry folks. You know, the idea of receptor occupancy and that leading to, things like potency, and then also concepts of efficacy, those all still exist. So all these things still exist. And we have this theoretical knowledge of all these different things. We understand gene expression. We understand how DNA goes to RNA, goes to protein, right? We understand all of these things. We just haven't done risk assessments. And so now imagine today, some person up on high comes to you and says, okay, you need to create some way of doing risk assessment. What are we going to do? How are we going to do this? That's your new task. That is what you need to figure out. How are we going to do risk assessment? So today, like I said, I'm going to share with you my vision for risk assessment. And I'm kind of curious how your vision might be different from mine. I think it's important that we go through these types of exercises every now and then, especially as right now we're in the midst of trying to figure out how in the world we're going to do risk assessments, in especially as we drive towards using these newer technologies that we have. What exactly are we going to do? So as part of my vision, it's probably no surprise for those of you who know me that I really want to make toxicology more quantitative and theoretical. In some ways, what I'm saying, and I can't believe I'm actually saying this, I want toxicology to become more like physics. Man, I just can't believe I just said that. But that's really what I'm envisioning. There's a lot of good things that happen in physics because they have such a strong theoretical bent. One of the things that they can do is they can go off into theory land and they can start playing with ideas, and then the applied physicists can then take those ideas and then test these hypotheses in the real world situation. And I think if we were to bring toxicology into that kind of fold where we were able to do more quantitative hypotheses in the theoretical realm of toxicology, we would then be able to actually test hypotheses in a better way. I think that would also help us bridge that gap with public health. One of the things that, and I'm not throwing stones at public health scientists, they do what they can, the best they can with the data that they have, which is extremely limited typically. But there needs to be a way that we can, bridge this gap, because there are things where, for the most part in epidemiology, unfortunately, they're forced to deal with correlations. And right now, we still have a lot of hard times trying to bridge that gap. And if we had a better theoretical understanding, we might be able to build better hypotheses that we could use to better inform the epidemiologists, or they could use to better inform us. And so, as I mentioned, some of the mathematical foundations will help us build better risk-based hypotheses. This, I think, is one of the big problems we have in toxicology today. And I'm not going to throw stones at any particular people, because I think it's more of a societal effect of toxicology research, is we're not doing a very good job of actually articulating hypotheses and then trying to test those hypotheses and stress test them to the point where they could fail. Instead, we tend to celebrate our successes. When our hypothesis comes out right, we then celebrate. And it's like, oh, that's a very, very, very good thing. We had this great understanding, and our understanding has now been confirmed by the science that we've done. And in reality, a lot of the studies that we're doing, they're too small. They're not done right. The stats aren't done right. There's lots of issues that then end up causing us to have p-values that are less than 0.05 when probably we shouldn't. But one of the biggest issues we have, and this is going to sound funny coming from me. So I've been cross-trained in stats and toxicology. And the first thing that a good statistician will tell you is, I don't really care what your p-value is. What I really care about is, do you know what's actually adverse? So if we're looking at alanine aminotransferase levels, right? We're looking at injury. If you can't tell me what effect size is actually adverse, a good statistician will tell you, then you don't do the stats. Because you can gin the stats up to give you a p-value less than 0.05 for the most part. But what really matters is that effect size. And so that's the first thing a good statistician will tell you is, if you have no idea what a biologically or toxicologically meaningful effect size is, then don't do the stats. You shouldn't even be doing the study. So for instance, with ALT, we know, if you're in the 20s, 30s range, that's pretty well normal, right? So 10 to about 30 is normal. Normal can go clear out to about 70. It's not until you get closer to 70 to 100 units of ALT that you're actually in the adverse range, right? So we have a pretty good idea as to what effect size we need before we say this is toxicologically relevant. Unfortunately, we don't have this for most things that we look at. So for instance, anogenital distance, right? We don't know what a toxicologically relevant effect size is for anogenital distance. We don't know what it is for litter sizes, things like, we don't have a great idea as to what is actually adverse. And so sometimes this gets down to, the classic debate about liver weight, right? Is liver weight actually an adverse event, this increase in liver weight, or is this increase in liver weight kind of more of a compensatory mechanism? Until we get a lot of those things sorted out, it's going to be really hard. But in order to get to quantitative toxicology, we need to start sorting these things out. So I think we as a community need to start having these really difficult conversations that we always avoid. And I think that's probably a very important thing that we need to do. And ultimately, once we start having these very difficult conversations as a family that we don't want to have, right? Once we have this intervention with ourselves, I think we can then start to make better predictions about toxicity. But if we're not going to have these family chats, then, we're not going to get very far with respect to NGRA. Precision environmental health, I think, is another key driver here as part of my vision. I think it's important that we be able to predict and understand how environmental stressors will impact each individual within a population. We do want to protect the most sensitive individuals in our populations. And many of you will be just flabbergasted at how many times I have to have a conversation with an attorney where they're like, well, you toxicologists, your safe values don't take into account, the most vulnerable in the population. It's like, no, they do. When I'm talking about an EPA value, it definitely does, or a Health Canada value, it definitely does. And it's kind of funny. I get that, like, in every deposition, they try to tell me that the values, the risk values that we create, aren't protecting the vulnerable parts of our population, but they are, and we need to continue to do that because it's important. So for me, in order to get, this is my 30 to 50 year forecast. These are the steps that I see that we need to do to get to eventually having a fully computational risk assessment and to having more human relevant risk assessments. Ultimately, what I would love to see is more genetic diversity in our in vitro assays. It's going to be really hard. But I think once we start going down that road of having more genetically diverse in vitro assays, we will be able to then say, yeah, our in vitro assays are actually covering the population. Because one of the issues that we have is, and this is a complaint I make with a lot of sociology studies, if you're only, you can't infer statistically beyond the population that you studied or the population that you sampled. There was an interesting article, I think it was in the Washington Post, about homeschooling that I was reading this morning while eating my breakfast. And it was kind of interesting because the sociologist who was studying the homeschooling, and he's a bit of a homeschooling evangelist, his study population was not representative of the general U.S. population that homeschools. His population was white Christian 2-parent households with fairly decent incomes. What we know, though, is that there are a lot of single-family households that are not white that are actually very poor that also homeschool. And so he's saying that homeschooling was doing all these great things and kids were consistently showing these high test scores. But the question becomes, well, wouldn't they have shown high test scores even if they were in the public school? Because these tend to be the kids who tend to do well on these types of tests regardless. And so that's one of the things that we have to remember is when we're using our in vitro assays are not typically genetically diverse. And so it can become an issue when we try to extrapolate what we're seeing there across the larger population. And, some people will say, well, that's why we have the tenfold uncertainty factor for, zero. That would be for human variance. And so, assuming the tenfold would work to help us bring that about, yeah, that's fine and all. But it would be better, and I think most of us want to move away from these default uncertainty factors and to actually have that data represented, have the variability represented within the samples that we're using. So getting to a genetically diverse in vitro, set of in vitro assays is going to be very important to get us there. We're nowhere close to that. Eventually, I'd like to see us getting into populations of digital twins. I think that's something that we could get very close to, maybe even sooner than the genetically diverse in vitro assays. Maybe I should swap where those two are on the number line here. Getting to a fully computational risk assessment, I think we're way far away from getting to a reliable fully computational risk assessment. I think we could have fully computational risk assessments today, but they certainly are not reliable, and I would not trust them beyond screening at this point. But eventually what I think is going to be the real future is if we can have the in vitro twins on a chip. And if we could, have a way of, having different chips that represent, a sampling of the population, a good sampling, a representative sampling of the population, that will get us eventually, I think, to the holy grail that we're all trying to get to. With human relevant risk assessments and NGRA. So in transitioning us from our current risk assessment practice into the future, one of the things that I've been thinking about is how we've strayed from some of our ideals. And so I'm coming up with this term, and I don't want to call it a framework because we've got frameworks for everything. It doesn't seem to help. So I'm not sure what I'm calling this right now, but the concept is high risk, HY risk. If any of you are from the Midwest of the United States, you may know of a store called Hy-Vee. This just kind of reminds me of the Hy-Vee name, which is a great grocery store. The HY stands for hypothesis driven. I think we need to make sure that our risk assessments remain hypothesis driven. And I've seen a lot of cases where they're starting to stray from that. And I'd like to really see, and I'm not going to name names on that, but I really want us to do better hypothesis-driven science. And when I say hypothesis, and I'll explain these in a little bit, but the key here is we need to be trying our hardest to what we call falsify the hypothesis, or to prove that the hypothesis is actually false. We need to make sure that our risk assessments are relevant, they're specific, and kinetically informed. So what do all these things mean? I touched on the hypothesis-driven just briefly. Turn specific questions that are driving the risk assessment into testable hypotheses and focus on disproving or falsifying the hypothesis. And we don't want to attempt to confirm the hypothesis. So a little bit of science philosophy here. If you look at Karl Popper's work, a lot of what you're going to see on this particular slide is informed by Karl Popper's work in the 40s, 50s, 60s, and actually may start even in the 30s. but a lot of his work. And what I'm specifically talking about here is we don't want to confirm the hypothesis because there's confirmation bias. And that was one of the things that Karl Popper really, really hammered on, is the fact that you can, through confirmation bias, you can identify all kinds of things that confirm your hypothesis. It's less important to confirm your hypothesis than it is to actively try to prove your hypothesis is wrong and then have it win. The way I like to think of this when I'm thinking about this is, I coach soccer, right? So my kids, my boys' team, they might just absolutely love the fact that they beat this other team 14-0, right? And don't blame me for running up the score because I tell them that they have to pass 15 times before they score, all this other stuff. But they absolutely love it. This is great, right? It's activating their dopamine receptors. They're loving it. They're loving every minute of the fact that they're winning, right? But was that a real test for them? Playing against this team, that wasn't a real test for them. They're not learning anything from this. They're not getting anything out of this, right? What I prefer is the games where maybe they don't win, but we played somebody who was really, really hard. We played a really hard team that made them really work for that ball, right? We played a team that, is forcing them to rethink some of their assumptions, forcing them to really pay attention to the game, really study the other players. That is what I want. And that's what we want in science. We don't want our hypotheses to just go, through easy tests where they aren't actually stressed at all. That's not what we want. We want to make sure that these hypotheses are correct. And the only way to do that is by forcing them to play a really hard team, right? So that's what the falsifying is about. We're not going to just gin up a study where, we have a small sample size so we know that we're going to have increased false positives, and typically people don't do that on purpose, but that's what ends up happening. With small sample sizes, you end up having a larger degree of false positives. So what you do instead, and Karl Popper is the one who first came up with this terminology, is severe testing. And it's a twist on statistical testing that isn't taught. Deborah Mayo has a book came out, I believe it was in 2019, where she actually comes up with a statistical framework for severe testing. It's absolutely fabulous. It's something that I'm going to start trying to write a little bit more about to educate the toxicology community on this better way of testing. Because if we adopt Deborah Mayo's severe testing paradigm, what we're doing is we are able to demonstrate the fact that, yes, this experiment that we did actually had a chance of falsifying this hypothesis. When you have small sample sizes, you don't have a chance of falsifying the hypothesis. It's just not going to happen. You're not stress testing this hypothesis. And that's really what we want. We don't want to have these easy wins. We want to have these cases where the hypothesis is really put to the test, right? Because otherwise, what's the point? Relevant. We want to ensure that the data is relevant for the population of interest. Genetic differences exist across populations. We know this, right? We want to make sure that the genetic background of the study population matches the population of interest. So, for instance, can I use a study that was done in China to inform me about what happens in a population in the United States? The answer is maybe. It depends. It depends on a lot of things. So the confounders that we have in, let's say, a Beijing population are much different than the confounders I have, let's say, in a rural North Carolina population, right? Our air quality issues are much different. We're going to have very different genetic background. We're going to have very different, social background. So there's a lot of things that make it kind of difficult to extrapolate from this Chinese population to a rural U.S. population. That's not to say I can't use the data, but that is to say that I got to be very careful when using the data. The other thing that I want to make sure people are aware of is your sample size need to be large enough to replicate the population characteristics. I don't know why, but for some reason, small sample sizes seems to rule the roost in toxicology. I have some suspicions, but I'll talk about those at some other time with people if they really care, and we can exchange our thoughts on that. But I want you to be aware of what was tongue-in-cheek called the law of small numbers. The Nobel Prize-winning economist Kahneman coined this phrase, the law of small numbers. And it's the idea that people believe erroneously that small samples are going to replicate what happens in larger populations. The law of small numbers is actually, in many respects, the thing that drives the gambler's fallacy. Those of you who aren't familiar with the gambler's fallacy, let me just fill you in. The gambler's fallacy is the idea that, I've done 16 straight losses in my video poker game, but I'm going to play this next one because game number 17 has to be a winner, right? That's the gambler's fallacy. Game 17 doesn't have to be a winner. And when people, and I've been to casinos and people try to argue this one with me, it's laughable. They'll say, well, you look right here, the odds of winning, with a pair in video poker is, X. It's not bad. But the thing I have to remind them is, but every time you play video poker, it's actually independent of all the previous times you played. And that's what people forget. These are independent draws. It's not like you're playing blackjack. With blackjack, it's a little bit different, right? Because with blackjack, they actually have brought together typically 7 to 30 decks. And so there is some conditional things going on there. There is a lack of independence when you're playing blackjack at the table, although it's not a great deal of independence. But when you're playing video poker, every time you play, it's a new game. Each game is independent of the previous game. And so that's kind of where this whole idea of the gambler's fallacy comes in. But people do this in science as well. They're using these small sample sizes and they're trying to say something about what happens at the population level. At the end of the day, even if you don't know that's what you're doing in your study, that's what you're doing, because the inference is being drawn back up to the population level. We want to be specific. We want our risk questions to be things that can be answered. And we want them to be answered very specifically to help inform some kind of risk management decision. And we want to focus on what information is required to address these questions. And to some degree, what's the value of this information? Is this information that is going to be very valuable to the risk manager? Those should be prioritized before things that really aren't going to move the needle at all. And lastly, this is a bit of a pet area of mine recently, is kinetically informed. So for those of you who've been following me on LinkedIn for a while, you know that we've been publishing, Chris Borgert, Claudio Fuentes, and myself have been publishing a series of papers on the KMD, the kinetically derived maximum dose. And we just recently had another paper published. I should have updated these slides with that reference as well. But we've been publishing a lot on this, and our way of calculating the KMD is different from some of the ways that have been published in the past. But to us, what it really demonstrates is the fact that at the end of the day, we do need to have this kinetic information, because we need to stop doing the maximum tolerated dose testing for a number of reasons. It's not informative. Typically, these doses are well outside the human relevant range. And so therefore, they're largely unethical. Now, for the person, because this is the argument that I get thrown back in my face when I say that these are ridiculous doses, somebody say, yeah, but we need to know what's going to happen, if some catastrophic spill happens or there's an explosion at a chemical plant. And so MTD informs us of that. And I'm going to argue, no, it doesn't. I've done emergency response toxicology for years. And I'm here to tell you, no, the MTD doesn't inform me about anything, because guess what? If it was safe below the KMD, and then the KMD is where we start seeing toxicity, that MTD is much higher. So I know bad things are going to happen, right? I don't need an MTD test to tell me that a chemical causes hazard. I know that. I know that there's a dose at which all chemicals are going to be problematic, right? And so I don't need an MTD test to tell me that. Typically, most of the tests that we do that are not MTD will get me the information I need to know. I'll have a no AL, a low AL, something like that. But once you get past that KMD, it doesn't matter. The mode of action is likely going to change due to the saturation and elimination kinetics, right? So here I've got a couple examples. Ethanol, this is the classic one we like to talk about when we talk about KMDs. Alcohol is absolutely no fun below saturation of the elimination kinetic mechanisms. Once you get below the KMD for alcohol, alcohol is absolutely boring. Nobody would want to drink alcohol if the KMD were any higher, right? Aspirin's another interesting one. Aspirin, once you saturate elimination kinetics, it becomes lethal due to the anion gap metabolic acidosis, which will then lead to pulmonary edema and eventually death. So we know that the KMD is important. And so this is just part of the thing where I'm just trying to stick this in to say, let's stop doing MTD. It's unethical. It's pointless. It doesn't inform anyone. You talk about something that doesn't help a risk manager. MTD is it, when we could do a KMD, which is far more reasonable. Anyway, so that is high risk, hypothesis-driven, relevant, specific, kinetically informed. And again, that all ties together, these concepts I'm coming up with respect to this technological future. Now, I'm not going to go into each one of these steps individually and talk about them today. And so what I want to do instead is I want to start with, in order for us to get to this envisioned future, we need to start with what we have available today. So let's talk about that. So today, what do we have available to us? We have in vitro assays. And how are we going to use these in vitro assays? Well, I envision that the best way to use them for risk assessment purposes is something that has been emerging over the past few years, and that is the quantitative adverse outcome pathways. AOPs, most of you are familiar with, to me are good for hazard identification. I don't, hazard identification, fine, that's good, right? But what I care about here is risk assessment. In order for us to get to risk assessment, we need quantitative adverse outcome pathways. And there's a rich literature on this. I was part of one of the first groups that started writing on this. And then there was a bunch of groups from Europe that started expanding on some of these ideas, some really good papers out there right now. I suggest you go out and read them. But what I want to do is I want to just, as an example, look at AOP 411. Partially because it amuses me that it's 411, and here in the United States, 411 is the number you used to call for information. And so that just amuses me a little bit. But the thing that I really want to bring out is the fact that in this, here we have the adverse outcome pathway. It starts with oxidative stress, and it'll go all the way down to decreased lung function. So this is the example that I'm going to use to try to talk a little bit about how we go from an AOP to a QAOP. Now, I'm not going to show you a final QAOP here, but what I will say is we're working on a paper right now that kind of spells it out for 411, where these KERs, right, these key event relationships right here, the arrows, these arrows become mathematical functions of some kind. Some people do Bayesian network models, and so these are the transition probabilities from this state to this state. In the particular group that I'm working with right now, we're actually using full-on mathematical models that explain going from oxidative stress, let's say, to decreased FOXJ1 protein expression, or activity, I should say, and then going from this decreased FOXJ1 protein activity to decreased modal cilia number and length on down the line. So each one of these KERs is a mathematical function in the QAOP that we're actually writing up the paper on right now. And hopefully we'll submit it in January or February. We'll see how that goes. So kind of a callback to what the title is. In my mind, we then, quote unquote, paint our in vitro assay data onto the nodes of the QAOPs, building these mathematical models that I talked about that represent these key event relationships. So what I believe is that this will help us to ensure we have internal validity across the series of mathematical models. So the QAOP itself as a model, and then all of its models that it subsumes as well. And so if a KER's mathematical model is not able to accurately predict the next key event, then we know we've got a problem, right? So we need to make sure that the KERs are actually functioning properly, and in vitro data is going to help us do that. The data used to train and validate the model, is going to be very important, and that's information that you'll want to try to make public so that other people can also assess your model's performance. And then I think a big thing that we don't see as much in toxicology anymore, except for GLP studies, is the use of positive and negative controls to help us validate the overall QAOP, and that N at the end is network. So I'm basically acknowledging the fact that QAOPs should not be these straight linear things; they should be networks, which actually AOP 411 is kind of representing a network. And so these are important aspects that I think we need to make sure that we have. And I'll go more into what we call V&V, which is verification validation, in a few more slides. So for me, the best practices for QAOPs, and I've got a paper that should be submitted probably January, February timeframe as well. We really need to do a full-on causal analysis, and then again, what I mentioned before, the verification validation. And I'll give you a lot more on the V&V in a little bit, but first we're going to start with causal analysis. So causal analysis, as I'm talking about here, is based a lot on philosophy. It is not, as you may have just seen just now, it is not built on the Bradford-Hill criteria. Anyone who's actually taken a philosophy course focused on causality, which I chose to do a long time ago, will know that the Bradford-Hill criteria are completely insufficient. They're unreliable, and it's not a causal framework. And here's the best part. Sir Austin Bradford Hill said so. He said this. He said, I am not a philosopher. I am not going to try to, make some kind of philosophical argument or a statement. These are just my observations. And he also said that they shouldn't be used in the way that they're being used today, which is kind of like a check the box exercise. He was very clear. These are just observations. This wasn't even in a formal paper. This was in a paper he wrote as the president of some society as a report. So, like I said, for causality, we really do need to go back to the people who really study this a lot, and that's to go back to philosophy. If you don't want to go back to philosophy, cool. Let's instead go to the courts, because at the end of the day, these risk assessments that we're doing are going to get litigated at some point. We're seeing it with glyphosate, right? You can name any, asbestos, all these things. At the end of the day, in court, when we talk about, it's called toxic tort. Tort means injury. We're talking about cases focused on injury due to exposure to chemicals. The key questions are general causality and specific causality. General causality means, is there evidence that this kind of an exposure will cause this kind of disease that the person states that they have? That's general causality. Specific causality is, within this particular person, is there evidence that these particular exposures resulted in this particular disease and it wasn't some other cause? That is what causality ultimately answers. And in philosophy, that is what a lot of that philosophy literature on causality is what judges actually use and are trained on to make these determinations of causality. And it's what they instruct the jurors to use when they're making these assessments about causality. So, just a few reminders. I call this step 0. Counterfactuals are critical. So, this is different from a historical counterfactual in some ways. In this case, what counterfactuals mean in the philosophical sense of causality is a counterfactual. If you're looking at specific causation, it would be, I have this person who's been exposed, and now I have the same person and they're not exposed. And the question is, well, not the question, the point is of counterfactuals is to say, but for this exposure, can I prove that they would have this disease? So you're getting at the question of, did this particular exposure cause the disease, or set of exposures cause the disease, or was this person predetermined to get the disease? So the counterfactual of the person is someone who didn't get the chemical exposure. Did that person who did not have the chemical exposure, the counterfactual, would they have developed this disease anyway? That is the true crux of causation in philosophy and in the law. Every time I go into a courtroom, the thing that I need to address is that but-for question. But for this exposure, would they have developed this disease? That is what we need to really focus on. And if we think of toxicology in those terms, then we say, oh, well, toxicology kind of addresses these things through experiments, right? But here's the catch. And this is the crux of experimental design. Experimental design aligns very well with the philosophical underpinnings of causality, mostly because the philosophers have thought a lot about experimental design. A lot of the experimental design folks were also talking to the philosophers at the time. So here's what happens. An experiment is a counterfactual if the only thing that is different between the control group and the experimental group is the exposure. Okay? The only thing that's different. So we need to get the control group to be as identical to the experimental group as possible so that the only thing that varies between them is the exposure. That makes the control now a counterfactual. Another reminder, we can't reliably extrapolate beyond the study population. This is what I call the first rule of statistical inference. You can't. It's simply, you cannot do it reliably. You cannot say, oh, well, I got this population and they look completely different from this other population. So like, I can't make inferences about a group of 10-year-olds, so like my son's classroom at school, I can't make inferences based on them and then say, well, that is how this group of first graders in my daughter's classroom are going to respond. It doesn't work that way because now we have one population that is completely fifth graders, and I'm trying to use information about fifth graders to say how a group of first graders are going to respond. It doesn't work that way. We talked about the law of small numbers. Just a reminder, beware of that. And then lastly, this is something that a lot of people take for granted. AOPs and QAOPs are not actually causal chains. And they don't become causal chains just because we say they are. When I've gone through a lot of these AOPs in the AOP wiki, there's insufficient evidence to state that this is a causal chain. And the reasons why is because in large part, we don't have good counterfactuals, but the even larger part is the fact that they aren't actually testing in isolation the different, things that they say are happening. So for instance, there's not a lot of reliance on dominant negative research. So if you want to say that, protein X is responsible for something, it's not sufficient to just use an agonist for protein X. You also need to shut down protein X in the presence of the agonist, right? So you need to have agonist plus dominant negative or agonist plus antagonist, something like that to shut down protein X to then say, oh, yeah, so when you remove protein X, guess what? Then you remove this effect. That needs to be done in order to say that something is actually causal. And we don't have that, right? So just because it's an experiment doesn't mean it's sufficient evidence of causality because we really do need to prove that but for, and we need to prove that but for completely. So going from a AOP to QAOP, the first step is to convert it into a directed acyclic graph. For AOP 411, this is really easy because directed acyclic graphs means that you have arrows that only go in one direction. So all of our arrows are only going one direction. That's good. Acyclic means we don't have any cycles. So for instance, if we had like a feedback cycle or a feed forward cycle, then we don't have a directed acyclic graph. This does not have a feed forward cycle or a feedback cycle of any kind, right? Or I guess, yeah, it doesn't have a true feed forward cycle because that would be like decreased FOXJ1 protein, comes back on itself and causes more decrease of protein activity. We don't have things like that. If we did have cycles, the way that we break them to still have a DAG, or directed acyclic graph, is we introduce a time component to it. And so that's how we can break cycles and convert them into a DAG. We don't have that in this case, so we'll move on. So next thing that we do is we convert the DAG to a structural equation framework. This gets a little bit more complicated. I'm not going to go into all the nitty-gritty details of this. I could teach an entire semester course on structural equation framework and why it's so awesome. But I'll give you kind of the highlights. So if we start here with the MIE, oxidative stress, this is kind of a state model. So 1 means it's activated, 0 means it's not. So the MIE will be activated, so there'll be 1 if the system is exposed at a sufficient dose to activate the decreased CFTR function, and this symbol means and the decreased forkhead J1 protein. Else, MIE is 0. And you do this for all of these nodes in here. And so that's what you can see all this is. All these different nodes, okay? This is just a reminder. There's this thing called the no backtracking counterfactual rule, which basically says if there's a decrease lung function, so if we have the AO, then the MIE oxidative stress was sufficient to activate the AOP. And that statement's false. And it's false because there could be any number of reasons why there could be this decreased lung function. We have to make what's called the open world assumption. So we can't assume that the AOP is complete knowledge. Unless you have an AOP network that you state as complete knowledge, you really can't do that. And so then, therefore, we can't really make the, we have to be careful with the backtracking counterfactual rule. So the reason why we created those structural equations, why we went through the SEF framework, is to identify places where we can start having preemption events and then start mathematically utilizing those preemption events. So what's a preemption event? We would ask ourselves, okay, so is oxidative stress the only way that we can get to FOXJ1 protein activity decrease? Is oxidative stress the only way we get to decrease CFTR function? Are there other ways we could see decreased ciliary beat frequencies, et cetera? And as it turns out, for decreased FOXJ1 protein activity, yeah, there is another way you can get it. You can get it through decreased P73 activity. Now the question becomes, is this decreased P73 activity due to oxidative stress or not? Well, there are ways of getting this to be decreased, not through oxidative stress. So you could have an arrow from here to here, but that's also not complete. There are other ways of getting this. And so we do have ways of preempting this particular AOP. We could also increase this external to this AOP and shut this off, even though this is true. So there's a lot of preemption that we have to consider that may not actually be in here when we go to convert this to a QAOP. And that's going to become important in the verification and validation steps. So verification is focused on reliability. When we take things to court, the judge wants to know if something is reliable. How reliable is this information? So this becomes important for court. This becomes important for making all kinds of decisions. If it's not reliable, we shouldn't be using it. And reliability really means, are these results trustworthy? And something I'm going to mention is the key to reliability is orthogonal data sources. So what does orthogonal data sources mean? Orthogonal data sources are data sources that are measuring the same thing, but they're doing it in completely different ways. So the easiest example that I can give you is if you were measuring, let's say, FOXJ1 protein activity, there might be multiple ways of measuring this particular kind of activity. There might be different assays you could do to measure this to see if you come to the same conclusion or not. Another example is, this isn't necessarily a biological example. If we have a case where somebody was stealing from an ATM at a 7-Eleven, and let's say like the 7-Eleven only has one camera on this ATM, and this camera was such that you couldn't see the person's face, could you then reliably say, pick the person out of a lineup and say that that was the person who was robbing the ATM? Probably not. But if you had 4 or 5 cameras all focused around this ATM's area, where you can see the person's face and you get a relative idea of what their height is, and you have a very clear view of their clothing from different angles, it becomes a lot harder now for that person to say, well, that wasn't me, right? And so what that is that is, it's perhaps the same modality of information. It's video cameras, but they're measuring the same event from different angles, from different ways. Those are all orthogonal data sources. Orthogonal data sources are actually the true key to increasing the weight of evidence of something. You can take something that's very low that has a very low weight of evidence. But because you have these other ways of measuring it, you can increase the overall weight of evidence to some degree. And so these orthogonal data sources are going to be important. If I just have one assay measuring a key event, that's not going to give me a very good idea of the reliability of this key event being activated. I want all these other things also telling me the same exact story. Okay, now I believe it a lot more. And so the reliability, though, also requires, and this is something that tends to get overlooked and not talked about, is that the assays that are being used to measure the key events within the AOP actually have to operate through the AOP or the QAOP. And this is something that gets overlooked a lot. So if you're measuring a key event, but you can get to that through other means other than the QAOP or the AOP, then you're not actually measuring the key event associated with that AOP in a way that makes this reliable, right? So we need to make sure that whatever assay you're using is actually measuring that key event via the QAOP or the AOP. So the information flow is the same. Now, validation is where we get to fit for regulatory purpose. So are the outputs a reliable prediction that are useful for regulatory decisions? What does validation look like internally? Where I used to work at the Army, we would have red teams. A red team would be a team that plays, in this case, the part of regulators, and they would be very skeptical, or they would be, basically they're trying to represent what the regulators would be. In a soccer context or American rules football context, it would be there are teams, especially at the NFL, that they aren't your normal everyday players, but instead they study all the other teams that they'll be playing. And so on Wednesday, they're going to study the team that they're playing on Sunday, and they're going to act like Sunday's opponent, right? So that's where it came from. Well, it came from the military first, but anyway. Then we're going to ask, the validation is going to ask questions. They're going to probe the AOP, or the QAOP. They're going to look for problems, and they're going to ensure that there's this level of trust. One of the key things they'll be looking for are these orthogonal assays. If you don't have these orthogonal assays, that's probably going to decrease a lot of the trust. This is going to require scenarios where the QAOP must be valid and reliable under all of the scenarios. It's not possible for it to be reliable under every scenario, so we're going to look at the ones that are most relevant to the regulatory question. And then that's the kind of stuff you're doing internally to pregame what happens once you go to the external regulators and you start having the actual discussions with them to gauge buy-in. The hope is that by using an internal process and having a red team go through this first, you'll have a much easier conversation when it comes time to talk to the regulators. So I kind of mentioned this before, and I just want to harp on this again. I was on a podcast, the Zealous Advocate podcast a few weeks ago, and one of the things I brought up was I think a game changer for toxicology and for environmental health is going to be digital twin technologies. The ability to create a digital twin of any person, with their permission, of course, right, is going to revolutionize precision medicine and environmental precision health, because it's going to allow us to expose this individual digitally, so in a computer, to things that we would never ethically be able to expose this person to, and to begin to understand how they might respond. This is going to be a game changer for litigation, being able to take information about a person. Today, I know attorneys today who are already able to ask a judge for a person's whole genome, and they will do whole genome sequencing, and they will look for familial traits of cancer. I think in the future we're going to be able to do something similar to like this in the litigation space. This will be a game changer because it will allow the people who make decisions in court, the judges and the juries, to actually see that this person's exposure, what it could actually have done, and did it actually result in this, right? So it'll clear up a lot of those questions. It'll also help us with environmental justice issues. We'll be able to have a population that looks like this, and we'll be able, that looks like the impacted EJ community, and we'll be able to expose them, from birth to whatever time period we need to, care about, to the exposome that they have, and see, okay, so what happened, and then we can have also an untreated group, our true counterfactual, and follow them through time and say, the exposures did cause this disease, or no, the exposures did not cause this disease. I think the other thing that's going to be really great about this, though, is we can't stop a lot of exposures that we have, but what we can do is maybe we'll be able to work with our environmental health medical practitioners and begin to craft precision medicine type of remedies to help them either live with the diseases they have or to cure and combat other diseases. So I think there's a lot of great things that could come from this digital twin technology. Clearly, it has dual use implications that can also be abused. When I was at the Army talking about human digital twins, this was always one of the things that was in the back of our minds, was the potential for a non-state actor or a state actor, because there are some who are a little shady, who might use this technology to try to commit genocide. That is clearly in the back of our minds. That is the dual use that we are very concerned about. So we would want to make sure that we safeguard people's information that we would use to make these digital twins, right? We don't want people having their genome sequenced and those genomes going off into the hands of an adversary or an adversarial actor. I mentioned how this is going to help in the courtrooms, how this can help with our actual health. The other thing that I didn't mention a few minutes ago is I could see us developing consumer industrial products that are less risky using digital twins, but I think we'll also be able to identify better personal protective equipment for people as well. And I think that'll be something that's going to be great. Ultimately, what I'd like to see beyond just digital twins is in vitro twins on chips. I think that we're constantly going to be, doing a better job with respect to predicting biology, but I don't think that we're going to be there within 30 to 50 years that we'll have complete knowledge of all the biology we need. So I think we're going to need to be able to develop in vitro twins on chips, and that is going to, take us a little bit further than where the digital twins can go. The digital twins are only going to get us so far because of our current understanding of biology. But as we improve our ability to extract different kinds of stem cells from people's bodies, I think we will be able to, perhaps get some adult stem cells and then take these, differentiate them in different ways to create these in vitro assays that are specific to persons. One day I see this happening in a hospital type environment where we will have this capability and we can just say, okay, so, these are the things that, the oncologist might be able to use to say, yeah, this is a great cocktail. You're not going to respond poorly to it, but your cancer is going to respond well and we'll be able to decrease your cancer risk, blah, blah, blah. Ultimately, that'll help us with the medical toxicity. I also think this will help us just in risk assessment and toxicology as well, if we can start banking these things and then creating, within the lab, large population studies as well. So I think we have a lot of good things that could come out of the digital and the in vitro twins going into the future. And I think that QAOPs are the first step to creating the digital twins, especially when we have these mathematical models. So imagine having a family of QAOPs that cover a broad swath of the toxicology landscape that we care about in, and making this in silico, right? So now we have a lot of these pathways, we have these mathematical models. That's ultimately how we're going to make these digital twins, which is why the QAOPs are extremely necessary for getting us to the quantitative and the theoretical end of toxicology. And then, like I said, I think the applied side, so if we're, going back to the physics example, the theoretical physics, is going to be happening on the digital twin front. I think the applied toxicology is going to be happening in the in vitro twin front. So one last thing before I take some questions and let you go. I just want to just remind you, this is what I think risk assessment looks like today, right? It's this beautiful picture. It's very static. It hasn't changed. It's not going to change until we start taking action to change it. This is what I think risk assessment is going to be like tomorrow. This, by the way, is an image I generated using generative AI. Digital twins, I think, are our future. I think this is where we're going to go. To get there, we need to have better assays. We need to have better QAOPs. And eventually, I think we're going to get beyond digital twins and get into the in vitro twins. And I think that's the technology that's going to take us further. Anyway, thank you, everyone. I guess I forgot to introduce myself earlier today. I'm Dr. Lyle Burgoon. I'm the president and CEO of Raptor Pharmatox. This is my contact information if you need to jump off. Feel free if you have questions. I'll be sticking around for at least a couple minutes to take your questions. So thank you, everyone. And it's lunchtime on the East Coast, so I wouldn't be surprised if people start jumping off. I haven't seen any questions pop up yet. I think the questions should be open. This is the first time I've used this platform, so hopefully it is working properly, but I don't know. All right, folks, it's I haven't seen any questions yet. So what I'm going to do is, if you have questions, let me see if I can bring that back up one more time. Oh, I do have a question. So Britt asked, regarding susceptible populations, how do we extrapolate digital twins to represent the broader population? That's a really good question. I think what I'm hoping is that we will be able to get digital twins for larger populations. That's my goal. I have some hope given how the whole genome sequencing went with the Brits. They got what was it, close to 50,000 participants. I'm hoping we could see something like that. I don't know how NIH is doing with their whole genome sequencing project, but I have hope that we might be able to get to, if we had even 10,000, I think we might do decently at getting the whole population. But the susceptible subpopulations is going to be tricky. If we could overestimate on them, I think that would be good. But that's going to be hard. So I think it's going to take a lot for outreach. Okay. Any other questions? And thanks, Britt. That was a great question. I hadn't thought about that yet. I'll just wait a couple more minutes in case there are any other questions that come through. This is the hard part about webinars. I could sing some hold music. Maybe that would be good. Maybe I should sing some hold music while we wait. All right, we have another question here. So how would this work when you deal with a realistic world with general population exposed tens of thousands, a synthetic and natural hazard simultaneously? Yeah, no, that's a great idea or a great question. I think I'm hopeful that we'll be able to get some better data from the exposome studies. I know that right now NIH put out a what was it? R20 or not R25. Anyway, they put out a call for proposals for an exposome center that would coordinate across the world, actually. And so I'm hoping that from those efforts we'll get a better idea as to what exposures are actually looking like. Mixtures is a big issue. I think mixtures is probably our next biggest problem that, funnily enough, we've been talking about for decades, yet we've done nothing about for the most part. So I'm hoping that this will mean that governments are going to be putting more effort into mixtures research, and we'll be able to get a better handle on that. I think that is a great question, though. I got a question here about articles to read more about QAOPs and digital twins. There's a lot of articles on QAOPs. Rory Connolly, I think, wrote the first one. And then I was on a couple with Ed Perkins leading those. And so if you go to, well, nowadays I go to Google Scholar because PubMed is not working as well as it used to. If you go to Google Scholar and you look up Quantitative Adverse Outcome Pathways, you'll get a lot of papers on QAOPs. In the medical area, we're starting to see more papers on digital twins right now. So I would say go to Google Scholar again, Google digital twins at Google Scholar, and maybe even PubMed, you might find a bunch. Some of these are more in the computer science realm, actually. There's a lot of computer scientists who are interested in digital twins and are working with the ones that I'm really familiar with are the oncologists. They're really hot on digital twins. Yes, is validation truly possible? Genetic variation over time. Yeah, that's so. Okay, I got to put back on my evolutionary biology hat. That's a good question. I don't have a good handle on how much genetic variation there is over time. I think validation is possible if we soften it a bit, right? Because there's different degrees of validation. I think there's fit for purpose validation, kind of the good enough philosophy that we tend to use in engineering. And so I think we can get validation that is good enough. Genetic variation over time, I just don't have a good handle on that. So that's a good question. That's, I need to think about that some more. That's a good question. All right, everyone. It's 12:07. I don't see any more questions coming in. Thank you, everyone. Thanks for those of you who asked questions and those of you who stuck around. I hope you have a nice rest of the year. I hope you have a nice and happy, prosperous new year. And if you have more questions, you can find me on LinkedIn. You can find my email. It's pretty easy to find. But anyway, thank you, everyone, for being here. I really appreciate it. And thanks for sticking it out. Have a great day.